Hey, welcome to Chapter 5. In Chapter 5, we're going to be looking at derivatives again, but this time we're going to be focusing on exponential functions and trigonometric functions. So we're going to do a quick review of some of those skills before we get into the derivatives. So first up, just taking a look at your exponent laws. A lot of these are from grade 9. And then I think one of them is grade 10, and then into advanced functions with the logarithms. So the first one, when I'm multiplying two powers with the same base, I can just add the exponents. And then when I'm dividing two powers with the same base, I can subtract the exponents. When I have one power raised to a second exponent, so I've got one base, two exponents, I can multiply the exponents together to simplify that. And then when I have a negative exponent, we've seen this a lot with our simplifying in our last units, I can bring that down to the bottom and make the exponent positive. Or vice versa, if I have something in the denominator and I want to bring it up to the numerator, I switch the exponent, the sign of the exponent. When I have a fractional exponent, it turns into a root, and then the denominator of the root tells me, or sorry, the denominator of the exponent tells me the type of root. Now I can write this in two ways. I can put the m on the outside as the exponent, or I can put the m on the inside. Now when I put the m on the inside, sometimes I'll have to, if this base is actually a multiple term, like a 2x minus 1 or something like that, I would have to put brackets around it. So watch out for that. Sometimes I'll need to put that in brackets if there's more than one term here. All right, and then moving into some of our exponent laws from advanced functions. If I have a base number raised to log of the same base of m, then I can simplify this. Remember that when I have log base b of m, what this is saying is, what is the exponent on b that gives me the answer m? So I'm going to be finding that exponent, and then I'm going to be putting it on b itself, and so I'll get the answer m. You might need to listen to that. So the log in the exponent is saying, what is the exponent on the base b that gives me the answer m? So let's say that exponent is 4. And then I'm going to do b to the power of 4. Well, we just said if you raise b to the power of 4, you get the answer m. And so I'll get the answer m. All right, over here, again, we can simplify this. So when I see a log, what it's saying is, what is the exponent on the base b that gives me the answer b to the power of m? So remember that the first part of a log statement is saying b to the power of what gives me b to the power of m, and so of course it is m here. And so watching out for this, like when I have a b and a log b, they kind of cancel away, is kind of how we say it, and I get m. Or here, when I have the log b and the b inside of the log, again, they kind of cancel away and I get the m. All right, switching back and forth from exponential to logarithmic form, just to jog our memory, if I know that n is equal to b to the power of m, I can rewrite this in log form. And one of the things that I always emphasize is the log is actually equal to the exponent. So you can just write down the log is equal to whatever the exponent was in exponential form. So it's equal to m. The base of the exponent was b, so the base on the log is also b. And then the power itself, so the answer to the b to the power of m is n, so we call this the power, and that's what I'm going to take the log of. So make sure you revisit that. How do I go back and forth? We're not going to when we're in the quadmester mode, we're not going to actually look at the derivatives of logarithmic functions. It's one of the things that got cut this year, but you still need to be comfortable with log notation since it shows up in some of our derivatives of exponentials. Okay, next we're looking at trigonometric functions. So I want to go back and just revisit the curves. Sometimes this is going to be handy for understanding derivatives as well as solving and manipulating some of the equations. So we're talking first about our base curve y equals sine theta. Here we've got sine x, same thing. So it's in blue here. I'm looking at my blue graph. And then for the second part here, I'm looking at the cos graph. So I'll be focusing on the red graph. So in the blue graph here, the amplitude, remember, is the distance from the center or the axis of the curve to the top maximum point, or from the center to the bottom minimum point. So it's this distance here, or I can be thinking about it as this distance here. And so I can see that that distance is 1 here, and it's also 1 here. It needs to be the same or you do not have a sinusoidal curve. All right, and then the axis, that's the center line. So where is our center line? Because we know that these curves can shift up and down. And so here, our center line of our parent curve is right along the x-axis, which is a height of y equals 0. So the axis should always start with y equals. We already know that. The period of the curve is how long does it take one cycle to complete. So how long until I start to repeat myself. And so if I'm starting here on the sine curve, I go up, and I'm not repeating myself now because down is different than up. And here we go, that's the end of the cycle there. So that's a distance of 2 pi. So period is also a distance. And then taking a look at the phase shift. The phase shift is like the horizontal shift. And again, we're looking at our parent function here, so there is no horizontal shift. It's just 0. All right, moving on to our cosine curve. The cosine curve now, I'm focusing on the red bit. Again, the amplitude of the cosine curve I can see here is a distance of 1. So this is like a vertical distance, whereas period was a horizontal distance. The axis is like a vertical shift because it's telling me if I've moved the curve up or down. So if I had like the curve up here instead, then I would have a vertical shift, and I would have an axis here. It's like at about 2-ish. I didn't do a perfect drawing. But our original cosine curve has not shifted, so is y equals 0. The period of the cosine curve, so how long until we repeat ourselves again, I'm going to start at x equals 0 and just tracing along until I get to the point where I'm going to start to repeat the pattern, and then that again is at 2 pi. So it's a distance of 2 pi. And then our phase shift, again, we're talking about how far have we moved horizontally. This is our base curve, so we haven't moved horizontally. All right, so what happens if I have the transformation format? So I have an a multiplier in front of either function, sine or cos, and then inside the function there's a k multiplier and a d addition subtraction. And the k multiplier is factored out. That's important for me to get the correct phase shift or the correct d value. And then adding c on the outside. So what we're going to see here, hopefully you've noticed that amplitude is a vertical change, the axis is a vertical change, we already said phase shift is horizontal, and the period is also horizontal. So the vertical changes are going to come to the changes to the y values, which are on the outside of the function, outside of the brackets, and the horizontal changes are coming inside the function or inside the brackets. So the amplitude change is actually the a value here. If I have a multiplier in front, it's going to stretch the curve vertically, right? It's a vertical stretch. And so my new amplitude will be equal to the a value. It could also be a vertical compression if a is less than 1. And it doesn't matter if a is negative, that'll just give me a reflection, but the amplitude would stay the same as just the original value without the negative sign. All right, the axis of the curve, that's going to be y is equal to, and we're looking for the vertical shift. How much do we slide the curve up or down? And the vertical shift comes from the c value at the end. And then the period of the curve, that's going to come from either stretching this curve out or squishing it, compressing it in. So it's a horizontal stretch or a horizontal compression. So it has to do with our k value here. Remembering that we start with a period of 2 pi, and remember that the k value, we actually divide by the k value to find the change. So when the k value looks like 2, it's actually a compression, and the factor is 1/2. And so what I do is I take the original period and I divide by that k amount. Now, when k is a fraction, like let's say k was 1/3, then when I divide by 1/3, that's the same as multiplying by 3. And so I'll see a stretch. And then it looks like the factor would be 3. And then the phase shift, I'm taking a horizontal shift, and that comes from the d value in the brackets. Don't forget that it's the opposite sign. So up here I have minus d, and so it's going to shift positive d. All right, our first example, we've got an equation. We're going to state all of those properties for these particular numbers. So again, I'm thinking about the fact that these guys on the outside are vertical changes and these guys on the inside are horizontal changes. Remembering that my period is a horizontal change and my phase shift is a horizontal change. Amplitude and equation of axis are vertical. All right, so I'm just going to go in order. It doesn't really matter, but for the period is equal to 2 pi divided by the k value. So you might also find it helpful to write in that this is A, K, D, and C. Maybe that helps you sort out your thoughts. We're going to take that k value and divide by a half. Now dividing by a half is the same as multiplying by 2, right? Like if I have 2 pi divided by 1/2, when we divide by a fraction, we multiply by the reciprocal. So we're just multiplying by 2. And so I get a period of 4 pi. All right, next up is the amplitude. The amplitude is just equal to the A number, so we're on our way here. The amplitude is equal to 2. And then the axis, the equation of the axis, also a vertical change, so it comes from the outside of the function. That's the C value. And we do need to write that as an equation, so I need the y equals, and then the C value is -1. And then our phase shift. When I state this phase shift, I have to give the value and the direction left or right. So the phase shift coming from inside, the k value is already factored out, so I know that the positive pi by 2 is my d value. I am going to switch the sign though when I pull it out. So I'm going to go pi by 2, and I'm thinking about, well, if it looks like it's positive, remember I go the opposite direction, so it's pi by 2 to the left. So I would rather see to the left than negative pi by 2. I'm not sure if you know on the graph what negative pi by 2 looks like, so tell me it's to the left. All right, our next example, we're going to do some solving with trig functions. When you solve, you use the same sort of rules that you use for linear and for quadratic. So when I look at this equation, there's no squaring. And so I'm going to try to isolate the x. Now, when I isolate the x, I'm going to isolate the sine x. So there's no squaring or cubing, etc. So I'm going to isolate sine x, and then we'll work from there. If there was squaring, then I would set it equal to 0 and factor. And we'll see examples of that in future lessons when it becomes relevant. All right, so we're going to solve this guy. I'm going to rearrange. And so I have a multiplier of root 2 in front of the sine x. I bring it over and I divide it on the other side. And don't forget, we need this skill inside of this question here, because after you factor, you'd set each factor equal to 0. So you'd end up with something like this. All right, so I've moved it over, I've solved for sine x, and now what I'm going to do is use my special triangles. So using special triangles, I'm going to figure out what the angle is here. So remember that when I have something like this, sometimes people misunderstand what this means. Sine is saying compare the opposite and hypotenuse sides for the angle x. And when you do that comparison, you're going to get the ratio of -1 over root 2. And this is comparing my opposite and my hypotenuse sides. So this is the comparison. I want to know what the angle was. So I'm going to draw a quick picture of my special triangle that involves 1 and root 2. And this is our 45-degree angle triangle, or in radians. Remember, 45 degrees is the same as pi by 4. So in this chapter, we are using radians exclusively, but when we move into vectors, we're going to switch to degrees. All right, so I can see here that when I have 1 over root 2, that I'm going to get an angle of pi by 4. Now this is negative 1 over root 2. So what I've discovered here is that my related acute angle is pi by 4, and now I need to figure out what quadrant it's in. So I'm thinking about the cast rule here, and I know that the sine ratio is negative in these two quadrants. So whenever I'm solving for an angle, if they give me a ratio, there's always two answers, unless they restrict the domain of x. So what I have here, my first answer, again, the related acute angle is always between the x-axis and the terminal arm. So those are my related acute angles. My first answer, x1, is going to be a pi. Remember, there's pi radians on top plus a pi by 4. Now, if there's pi radians on top and I'm slicing them into 4 pieces, then there's 4 pi by 4s on top plus 1 more. That's 5 pi by 4s. And then on the bottom, the second angle here, rotating around, we're going to call this guy x2. Again, if there's 4 wedges on top and 4 wedges on the bottom, but I'm missing 1, that was 8 wedges in total, missing 1 is 7 wedges. So 8 wedges in total minus 1 is 7 pi by 4 wedges. All right, now this question did not give me a restriction on x. So sometimes the question will say something like where x is between 0 and 2 pi, and then I would be done here. But if there is no restriction at all, then this continues to repeat. I could just loop myself all the way around the circle and then head out to that first terminal arm, and I would have a second answer. Or I could rotate backwards if there's no limitation on negative answers. So I need to find all of the answers that correspond with these two terminal arms. So I'm going to think about the fact that the solutions repeat every period on the graph, or I'd be adding like a 2 pi circle. So I'm using the period to help me figure this out, right? And so my first answer is actually going to become all my x1, so all the angles that end on that first terminal arm are going to be 5 pi by 4 plus some multiple n of the period. So maybe I multiply, or maybe I add like 4 periods, or maybe I take away 3 periods, and that's going to give me an answer. And so, of course, I need to define what n is here. N is an integer. It can't be a decimal or a fraction number. It has to be a whole period. And so this says n belongs to the set of integers. All right, for x2, again, I'm going to start with 7 pi by 4, but I'm going to add some number of periods, so 2 pi n as well. And I've defined n here. You could do it really at any point as long as it's with both of these statements. So perhaps you put it over here, and we've got our 2 solutions plus the restriction on the n. You don't need to do this if they give you a restriction, though, on the values that x can be. Then you just have to pay attention to which quadrants you might be in. All right, have fun with your homework.